Welcome to our next session of Intelligent Machine Monitoring. My name is Jan Löken and I would like to present you today a case study with the topic impact versus impact. So what does that mean, impact versus impact? We will talk about different situations in case of a critical condition of a piston compressor, and we are talking mainly about the frequency domain. So impact versus impact means what is an impact if we measure that from 0 to 2 kHz only, and what is an impact if we take the complete range up to 7 kHz. We will do that today with a little introduction. After that we will go more in the basics, so why we are doing that, what is an FFT and how we analyze that with different analyzers like RMS or like the zero to peak. Before we go to case study number 1, case study number 2 and the conclusion finally, we will be at around 7 to 8 minutes just for your information. So let's start with a little introduction here. We are monitoring a piston compressor with different vibration loops, with pressure probes, with proximity loops. For our session today we will focus mainly on the crosshead vibration probe, which is installed here on the top or on the bottom. The other probes are important as well for the monitoring of such compressor, like the piston rod proximity probe, like the cylinder vibration probe, or like the dynamic pressure probes, but these grayed out probes are not so important for today. We will focus on this crosshead vibration probe, which is installed here in the area of the crosshead. This probe is not only measuring the crosshead itself, it will as well check the connected parts like the piston rod, the piston, and as well the area here from the crankshaft. So let's go into details what we are looking to. The summary of the crosshead monitoring shows us here that we are talking about an acceleration vibration probe. This vibration probe can be installed in various directions, depends on the space or depends on the design of the compressor. It will detect mechanical impacts, and we have the possibility to check different frequency ranges. As mentioned, this is the main topic of today. So what is important? Are the first 2000 Hz important, or have we to go up to 7000 Hz? And important as well is, do we check zero to peak or RMS? So that is the first question of today. What is the best analyze for crosshead vibration monitoring? We are looking to mainly the energy inside such impacts, as you can see here in the first example of an FFT spectrum. So here from 0 to 2 kHz you have some vibration impacts, but as well up to 7 kHz, and even later you see that vibration impacts are there. So the question for this session today is, what is the best filter option to get most out of the signal? We're doing that with different analyzers, so the 0 to peak analyze or the RMS. 0 to peak means simply the amplitude, so from 0 to the maximum, so that's the impact itself. And if we check the energy, we are focusing more on the RMS value, the root mean square value, because that gives us really the energy inside that impact. And as we know, the crosshead is a big heavy part, so we are not looking to the tiny low energy peaks, we are looking more to the real energy to understand, is it a critical situation or is the compressor in a good condition? So a zero filtered peak might work for some cases, but protection wise we are looking more to the RMS value. Let's directly jump in the first case. So we have here a standard reciprocating compressor, we have a 4-throw machine, 3 stages, it's a hydrocom application, and that one had an issue. Let's have a look to the good signals first, so how good crosshead vibration signals look like. Here on the top you see the raw data over 1 revolution, which are measured directly with that crosshead vibration probe. So we have the stroke here from the top dead center where the piston is completely in the top. It will move back to the bottom here in the bottom dead center and will move forward again in the top dead center. So this is really 1 revolution of the piston. And based on this signal we calculate the FFT signal, which is shown here below, and you can see already here in the red and green area that we divided this into the first 2 kHz and 2 kHz up to the maximum. Please keep that picture in mind. Here we are talking about the good condition, so everything is smooth. Even here are some impacts, these are normal for that compressor. If we now go to the bad condition, we see that there are new impacts. Other impacts simply increased on different positions over 1 revolution. But what happened to the FFT signal here? We see that the red area, so 0 to 2 kHz increased, and additionally 2 up to 7, 8, 9, 10 kHz increased as well. So if we focus only on this area, we might miss something. So in this example, it might be better to check 0 to 7 kHz just to see is that issue critical or not, otherwise we will miss something. If we check the pictures of that failure, so the customer was so kind and sent us some photos, we see, maybe you see that in the best way here on the right upper photo, that we have the crosset, which has already some wear. We are looking here to the small end connecting rod and as well to the pin, and all of these had already indications for a critical situation, so it was the right decision to stop based on the 0 to 7 kHz or even more kilohertz signal, which is recommended in many norms. Second case, good condition. Some vibrations are there, some areas are higher, some are lower, and the frequency domain here looks quite smooth if we look to the complete range from 0 to 7 kHz as an example here. If we now go to the bad condition where the vibration increased, we see in the raw data, something is visible here, so where the piston comes from top dead center and goes to bottom dead center, and as well on the other side where the piston moves back to the top dead center, we have a new vibration impact, or here in this example we have two new vibration impacts. In the FFT spectrum, if we focus on the area 0 to 2 kHz, we see a big impact. That's true. But if we focus only on this area, we will miss the impact here at 4 or 5 kHz, which is as well important. There is the main energy. This is the important topic to stop the compressor finally. For sure something happened here as well, but energy-wise that is not so much. Only the complete frequency range shows us the real energy of that vibration signal. Let's have a look to a different view, because we can do from the raw data as well as segmented signal. So we see here the good condition with the filter from 0 to 2 kHz. Some higher areas are there, some lower areas are there. And the good condition, if we take the complete range, looks already different. Some higher areas are there, and here as well a little bit. But in principle, both are good. And if we now check the bad condition for 0 to 2 kHz and for 0 to 7 kHz, we will see that the issue here in the lower frequency area with this filter is not so good visible. There are changes, but these changes are minor. And to put protection limits on these good condition, maybe you're a little bit too high and stop too late in that case, in that failure. But if we take the complete range from 0 to 7 kHz, we see that even the higher areas from the good condition increased a lot. And this makes it easy for the monitoring system to catch these frequencies, to put protection limits on that. So the final statement here is, in this example as well, take the complete range. It's better like to use only the small area. Two pictures from that second case issue. So we are looking to the piston rod. We see here the top area, so the fragments which are visible, it's already broken part. We see here the piston itself. From the top view, you see here where it was connected. So a really critical issue. And by monitoring only the low frequency areas, we can detect that, but it's harder to really define protection limits to avoid false trips, too early trips. So it's better to use the complete range to be really informed if something is going on. So what is our summary? We have different failures for sure. There are early failures. They are not so important for our story right now. That might be okay to look to lower frequencies only. But if we're talking about critical condition, critical recips which are having high vibration, then it's better to look to the complete range from 0 to 7 kHz, because otherwise we might miss something or makes our life difficult, because if we have just less information, it's difficult to put protection limits on that. So it's best to combine 0 to 7 with the RMS value. RMS is a real energy. It's not just an impact which might come from somewhere else, from a valve which is ticking and visible on the cross-head vibration probe as well. So it's better to use the RMS value to avoid that noise around that area. And as well, finally, the combination of everything is an important story. So not only RMS and not only 0 to 7 kHz. If you do both together, including the segmentation with the protection limits, then we are really fine to monitor this critical equipment in a good way. So finally, thanks for your attention of our next session here, impact versus impact. I hope you enjoyed that, and see you next time. Bye-bye.